Has anybody tried to get the GMS site license working on your computer?
Yeah.
It works, but the files that you gave us to download on campus are RAR files. And I guess you need some application to open them or extract the files.
They're compressed files. Yeah. Yeah. What GMS does is makes a lot of files that kind of clunky to deal with all of them. So I bumped them all up. That's not some. It used to be that you just would click on that and it would be a Windows application that would open it. But that's not happening.
Yeah, well, apparently download some app or something, or I don't have it, but I looked it up and it says it's similar to like a zip file.
Yeah,
Because it takes
Is it this RAR extractor?
Yeah.
Yeah, so you can download that.
I haven't tried extracting the files, but
Okay.
I've worked with RAR extractor before, so.
Okay, so just like go on Windows app and
It should be
download.
open, it should be a free app, I think, right?
Okay, cool.
Okay, good. So
It's
if,
not,
yeah, maybe try that.
Okay, the RAR extractor.
If you have problems getting the GMS site license working, let me know. Hopefully that all goes okay. So got the homeworks 1 through 5 back to you. Was looking over the homework 5 over the weekend and looking pretty good. The first cut through those flow nets. It's always a challenge to get everything working. It definitely is something that takes a good bit of practice. So we'll get another chance to go over those once you go and do the solutions for them. In the model, you can go ahead and do them again. I went and did them, and I don't know. I made a video of this and posted it. I don't know if anybody saw that. Just kind of the iterative process. But I thought we were going just to go over a few things that were kind of the main issues that come up when we're doing this. So what I had was in the comments, I would put 90 or ratio. That was kind of the typical thing. And 90 degrees would be when when the flow lines and the equipotentials aren't crossing at close enough to 90. Usually I would point that out when it was, more like 30 degrees, or I don't know, maybe not that much, but just noticeably off from 90. One thing that I saw a lot that I just want to make sure everybody's aware of. So that rule applies for the streamlines and the equipotentials, but the no flow boundaries also behave. We consider them like a streamline. So the equipotentials, when they come into the boundary, they have to be perpendicular here. A lot of times people were drawing it in and it would just kind of go like that. But it needs to hit that boundary and be perpendicular. And the reason why is because if this is the equipotential, right? And so the flow is perpendicular to this line here, right? So it's going to be like that. And here it's going to be like that. But if we drew the equipotential coming in like this, then that means that the flow would be like that. And if it's like that, then that means that, we can break it down into vectors, so we can break it down into components. That means that there's a component of the flow at the boundary that's perpendicular to the boundary. But it's a no flow boundary, so can't do that. Flow at the boundary has to be parallel to the boundary. Okay, and that means that it has to be perpendicular. Okay. So yeah, these were some of the trickier ones where it was all converging onto that point. One of the things that I think some people kind of lost track of is, if you go and do the streamlines first and do the ones on the edges, then this one, the first one, ends up, being kind of conforming to this boundary. It's not gonna go, it's not gonna go like that, because it's not gonna bend that sharply. But it's gonna be kind of conforming to that boundary. And then this one also would be kind of conforming to the boundary. Sort of like this. What I was seeing is that there were some flow lines that were kind of going like this, so they were flaring out at this end, and I'm not quite sure, where that's coming from, but it's not really gonna happen when the flow is starting from here and all headed in this direction. So this was just, I think you could avoid that if you just realize that the one on the edge needs to be conforming, in a smooth way to the boundary. Okay. Another thing is that when flow lines converge, the equipotentials need to get closer together. Okay. And there's this ratio issue, right? Along the stream tube, the ratio has to stay the same. So if that's gonna happen as the streamlines converge, the equipotentials are gonna get closer together. Okay? It's a big deal because the streamlines will converge on wells, and wells are coming up in the class. We're going to spend a big chunk of time on wells. We use wells to get access to the subsurface, so they're an important feature, and the convergence of flow that occurs from wells will be a feature of the flow field that happens in a lot of cases. So for this problem here, this was probably the one that was missed the most. What is important to show on this one is equipotentials are streamlined like that, and then the spacing between the equipotentials is decreasing. A lot of people felt like the spacing should be even. And if that's the case, then the gradient in the hydraulic head is the same everywhere. But what happens is, with this, the spacing is decreasing, and that's because the gradient is getting steeper as you approach this well, because the flux is getting larger, because you have to get the water that's flowing to the well to go through a smaller and smaller area. So the flow per area has to be increasing. Okay. So it's clear on this one, the spacing is decreasing, and then other ones like this, the spacing would also be decreasing here and on the other page. Okay. Yeah, and notice, if some of you were doing it on a tablet, which is fine. When I do this on pencil, I kind of sketch it in, like this, because I'm doing that, and I bet you I erased these, I don't know, at least half a dozen times. So there's a lot of kind of iteration, and the thing that's important at this stage is to be able to recognize the problems that have been caused, to recognize the problems in the flow net, and then take appropriate action to redraw it and try again and have those problems be reduced, then converge on correct flow net. Okay, any questions on that? Flow nets. Okay. All right, so we were talking last time about the Piedmont, the flow system in Piedmont. And what I'd like to do is, I'll get back to that in just a second, but what I want to do is to take a step back and look at hydrogeologic conceptual models in kind of a broader sense. And the sketch that I've been drawing here, well, this is the typical sketch where I've just now added in this layer. This is a type of a hydrogeologic conceptual model. And it's showing the flow system, the pattern of flows, the distribution of aquifer materials. Here's a low permeability layer, and what the different properties are. Also, water quality and water characteristics are going to be part of it. So it's kind of a sketch of a picture with the important concepts describing the hydrogeologic setting. Notice, for example, the flow system goes like this, and then it has that jog in it. And this is something that we don't want to see in a flow net of homogeneous material, but it does this when it goes through. This would be a lower permeability layer, right? Because it's diffracting down into the layer. You can think of it like the flow wants to get through that layer as quickly as it can and get back into this layer. Okay, so this is a hydrogeologic conceptual model. It's an important way of organizing or thinking about hydrogeologic settings. So the geology in hydrogeology conceptual model is important because it's going to control a variety of important aspects. These key properties, the hydraulic conductivity and the porosity, will follow directly from the material that is composing the aquifer. If you take a step up in scale, the layering or the structure will affect the aquifer type, and this will affect the flow paths, the travel times, well yields. The geology is going to control the materials that the aquifer is formed from, the minerals, and the interaction between the water and the minerals will be an important control on the chemistry of the water. And the chemistry is going to play an important role in how the water can be used. If there's really high dissolved solids, salts in the water, too salty to drink, then you can't use it for drinking water. And if it's fairly salty, it might be too salty really to do anything with. You can't use it for agriculture if it's got too much salt in it. So the water chemistry, and it is determined by, at least important aspects of the water chemistry will be determined by interaction with the geologic material. So the geologic material that is in the subsurface to form aquifers varies with the region. And so we have different hydrogeologic regions where the areas where the geologic conditions are similar. So if we think of hydrogeologic regions, we think of like two main controls. One is going to be what the bedrock is composed of. And then the superficial aquifer, this is stuff that's on top of the bedrock that's not related to the bedrock. This is sands and gravels from recent rivers or glacial health. Okay, so we have as part of the department, we have well fields in bedrock, in the botanical gardens, and in a superficial aquifer in the Clemson bottoms. So we'll go to the one in the superficial aquifer later on in the class. So superficial aquifers that are recognized as major aquifers are deposited from rivers. They're unconsolidated sands and gravels, and here's one in Canada, but then here's one where you can actually see the sand deposited from the Copper River in Alaska. So it's I don't know, a few kilometers wide and elongate in that direction. Now,
This is where there are significant alluvial aquifers, superficial alluvial aquifers in the US. So we're here, and there aren't any of these black lines of these superficial aquifers. There aren't any of them anywhere near here. This is the Mississippi River, the Ohio River, and the Missouri River comes up like this. So those big major rivers are hosts for these alluvial aquifers. But then we also have this pattern here of these kind of fingers, these channels coming up to the north, and then there's kind of spattering up here. So the reason for that is because these alluvial aquifer systems, some of them were deposited by high flows that accompanied the last glaciation. When the glaciers came in, they came down to right here. This was the southern extent. And then when they melted, they deposited these thick sands and gravels in river valleys. So these are important aquifers where they occur. We don't have any of them in the southeast because we didn't have glaciers here. And there are a variety of other things that form them out west, but we didn't have the right conditions to form thick sands and gravels. We had the right conditions to form sand and gravel in river channels, and that's what we have down in the Clemson bottoms. But in the Clemson bottoms, the sand and gravel is about 10 feet thick, and that's not thick enough to qualify as a significant alluvial aquifer. So that's why we don't have any of them here on this map. This is what they look like. This is this river valley, and this thing that's called substratum is sands and gravels, and that's the primary aquifer. And then it can be covered in some places by silts and clays, and so that could create a confined aquifer. And then in other places, it's there's some fine-grained sand on top, and so this would be an unconfined aquifer. So in this river valley, we could have both confined and unconfined aquifers, and they tend to be, it could be a couple hundred feet thick in sand and gravel, so they're really good, productive aquifers where they occur. Okay, but they're not around here, so much for that. I wanted to cover those to be complete, but this is a map of the bedrock aquifers. And you can see there's a lot going on here, a lot of colors and patterns. So there are a lot of different bedrock aquifers in the US. We were right here, and we talked about the Piedmont. This is the Piedmont right here, and the coastal plain in the southeast. So what I want to do for the class is focus on the aquifer systems that occur in the southeast, and in particular in South Carolina. So we saw this, the Piedmont and the coastal plain, and then this is where we get into the Piedmont in particular. So one of the important aspects of the conceptual model is the geologic units that are here that are contributing to the aquifer system. And we saw that there were three: these fractured crystalline rocks, and saprolite, and a transition zone between them. And this is where we left off, the process of the formation of saprolite, where we have weathering of the main minerals, feldspar, biotite, and quartz. And these two weather to clays, and this one is pretty resistant to weathering. When this weathering process happens, you have some iron oxide formed, but you also have materials that are just simply removed, that are just dissolved out and removed. And as a result, you go from materials, these crystalline rocks have porosities of 0.5 to 1 or 2%. And then when you go through the weathering process, remember, clay has porosity of what, like 40–50%, right? Clay was the highest porosity of any of the sediments because of how the grains are stacked together, right? Remember that? Good, we could remember that by Friday. And so the clay minerals cause those high porosity, and then also the fact that you have material removed by dissolution, that also opens up the pore space from the materials that were there. So the saprolite ends up having quite high porosity. There's the weathering process, and here are some data. Okay, so this is the porosity as a function of depth, and here are the measurements. This is from one particular study, and you can see up here at shallow depths in the upper 10 feet or so, it's bouncing around between 40 and 55 or 60 or 40 to 55 maybe percent. And that is pretty much what it's going to be all the way down through the saprolite and into the transition zone. Maybe a little bit less variable in the transition zone, but maybe also just fewer points. So pretty high porosity all the way down to transition zone. But then when you get down to the rock, it's down here in a few percent. Okay, so that's going to be from the primary porosity in the rock, which is a percent or so, and then also fractures can contribute some to the porosity. So big change in the porosity. Here is the it's the permeability, and this particular paper gave it in fortunate units of gallons per day per square foot. So I mean that's I'm sure how to deal with that. So I converted it here to centimeters per second, and this would be 10 to the minus 6 and 10 to the minus 7 meters per second. And what we see is that in this plot we have a bit of an increase in the permeability and then a big decrease here when you get down into the fractured rock. And a lot of the values are between -5 to -4 centimeters per second, or -7 to -6 meters per second. So here's another data set from another study. This is a more recent study. And this looked at the two situations, one where the area is underlain by layer material like gneisses and schists, and this is where it's underlain by this more massive material like granites. And all of these places here are power plants where, you know, if you have a power plant, it's a big infrastructure, and there's a variety of construction going on, and there are also environmental issues. A lot of the power plants, many of these, I think maybe all of them, are coal burning power plants, and so there are contaminants associated with the coal ash. And as a result, there's been a lot of work done on the subsurface at these locations, and they have a lot of data on the hydraulic conductivity as a function of depth. So this is the saprolite, this is transition, and this is the rock. And what you see is a good bit of scatter, but it's right here in this range, 10 to the minus 4 centimeters or 10 to the minus 6 meters per second. And then when you get to the transition zone, it kicks up. So it's a little bit higher hydraulic conductivity. You know, this is 2, 3, 4, there's 5 times 10 to the minus 6 meters per second. And there may be an order of magnitude range. And so it's like 5 times 10 to the minus 6 meters per second, plus or minus 5 times 10 to the minus 6 or so, something like that. Plus or minus half an order of magnitude. Okay, in this other one where the site, these 4 sites here are underlain by more or more massive or rock that it doesn't have as strong a layering. And in this case, here's that same number, that 10 to the minus 4, and you can see it's bouncing around. Here's a site at Gaffney where at shallow depths it's really low permeability. But at these others, it's just kind of bouncing around this 10 to the minus 6, and we don't really see the same pick here in the transition zone. Okay, so this is probably the most complete data set that we have for what the hydraulic connectivity in the Piedmont is like. And this is kind of reinforcing that notion that the transition zone has a bit of a higher hydraulic connectivity than the saprolite and the rock. Unless there's this bedrock that is these granites or granitoids, in which case maybe that's not true. There are some of these sites, though, you know, these blue ones where it's just kind of bouncing around. So this, I guess the yellow one is what I drew as the conceptual model. So that's kind of what we're thinking, that the transition zone could be a bit higher connectivity, but you know, maybe not necessarily. Okay, so for properties, this is the properties of the rock itself. So we talked about gneiss and schist, and then these are some other crystalline rocks that occur in the Piedmont. And so here are the porosity values. This is the intact rock. So 0.01 would be 1%. So these are like 1 to 2%. And this is like a block of, not granite, but it would be a crystalline rock like granite, that stuff. And this is the porosity that occurs in between the grains. These are interlocking grains, but they're not perfectly interlocking. There's a little bit of space between them, and that's what you get. If you work out, remember the specific yield is always going to be less than porosity. And if you take specific yield and specific retention, you can add those together to get the porosity. So the specific yield here, less than the porosity, and the hydraulic conductivity is here. Okay, we said that the saprolite was around 10 to the minus 6. This is the rock at 10 to the minus 10, 10 to the minus 11. Okay, so 10,000, 100,000 times less than the saprolite. So saprolite, remember, it starts out as this stuff. And then when it weathers, it goes from 0.01, 0.02 up to 40 to 50%, 0.4 to 0.5 in porosity. And this permeability goes from 10 to the minus 10 to 10 to the minus 10. Okay, so here's the summary. There's the K of the saprolite and also the shallow fractured rock. And that's several orders of magnitude higher than intact rock. And we take these data and translate it into transmissivity, about 10 to 100 meters squared per day or less. Recharge, these data here are from the USGS, and it's like 3 centimeters to 3/10 of a meter. So it's like this to like that for the recharge in the Piedmont. We've done a variety of analyses here, and we find, I mean, this is a reasonable range, but we find it's probably more typically around like 0.1 to 0.2, something like that, meters per year for the recharge. And then this is kind of on the high end of the well yield that we find in the Piedmont. So those are some of the properties. The flow system we have what's called a local flow system typically in this area. And the local flow system means that the water that recharges here is gonna discharge to the local stream, the nearest stream. And here it's gonna discharge to the nearest stream, where this is the groundwater divide. Okay, so the drawings that I've been making with the cross section where we've got the simple cross section and the flow line, that's a local flow system. The groundwater is discharging to the nearest stream. So if we take a step back, here is one person's concept for what a cross section and surface, what a perspective would be on the hydrogeologic system. So here's the rock, here's the transition zone, and this is labeled regolith, and that's another word for saprolite. And here's soil, and then this is the water table. So what's shown here is the water table is in the saprolite. And it comes down, and the water table is going to be continuous with the stream here. The dimensions, so the saprolite thickness here is typically around 50 feet, but it's variable up to 150 feet, and some places I have a low of 10, but some places there's no saprolite and the rock is right there. That's fairly rare though around here. It's, I don't know, 10 feet or maybe 30 feet on the minimum. And then 150 feet, probably thicker than that in some places, but this is about as thick as I've seen it typically. And then this is the water table. So 20 to 60 feet depth. Now right here, of course, it's going to be less than that when you get right down close to the stream. A lot of places around here, though, the streams are deeply incised. So if you can be quite close to the stream, but it looks like this. So the stream is cut down. So it looks like that. Here's the stream. And then the water table looks like this. So you can be up here and be pretty close to the stream, but you still got to go down 20 feet to get to the water table. Okay, so that's a reasonable range for the depth of the water table. Another part of this is that they're righted fractures. They're these horizontal fractures that we saw last time. And there are some vertical fractures. And then this is a formation contact. So the water is transmitted through the fractures. And this is a vertical fracture zone. And the concept is that many of the streams are following vertical fracture zones because the rock in these fracture zones is more easily eroded here along the path of these fractures than it is here. If it's more easily eroded, then the streams will erode it and it'll be lower topographically. You can look at maps and maps in this area, and there are places where the streams are just, have kind of a meandering pattern, but then there are places where the streams follow just a straight line. And then maybe jog over and follow another straight line. And those are often interpreted as places where the streams are following the fracture zones. Okay, so these are some cross sections through areas with saprolite, transition zone rock. These are broken down into 4 different regions where 2 of the saprolites are kind of split out. And this is showing how they're distributed on the landscape. So one of the things that people have been interested in is how does the thickness of the saprolite or the depth to the bedrock vary across the landscape? You know, if you have more weathering in fracture zones and streams, is maybe the saprolite is thicker there. Or maybe the erosion is fast in the stream and all the saprolite has been removed and the rock is closer to the surface and the thickness of the saprolite is less. So you see both ideas. And here we actually get opportunities to measure it with these boreholes. And you can see that here's the low-lying area and there's the thickness. So we're kind of getting a thinner zone of saprolite down. This is the rock right here. And then we come up here and it gets thicker, but then it gets thinner. And I don't know, this is a little bit of a low-lying area, but it's not really a stream. And then it gets thicker and then it gets thinner here just on level ground. So, you know, there's some variability, but it's hard to really pin down just how it would be related to streams. And here we see something similar. Here we have thickness of the saprolite, and then we pick up this is the transition zone getting thicker. Here, it's pretty much flat area, but we have this thickening of the transition zone. Then as if we go and get a upslope, we get these different units coming in and out. So it's variable, but it's kind of hard to come up with rules of the variability that are followed consistently. Here's some other cross sections of the variation. So yeah, here's some others. So what, in my view, the thickness of the saprolite and the depth to the bedrock is variable across the landscape. And in some places it thins towards the stream, in other places it doesn't. Some places it thickens up in the uplands. So it's hard to generalize. It's probably a result of interaction between the surface system and the rocks in the subsurface, which are highly variable. So what I want to do now is draw the conceptual model for this area, which will be a sketch that has these different things in it: the geology, the water table, flow system, what the scales are, and what the properties are. Okay. Now, I've done this. I will guarantee that this will be on the next exam, and also on the final. This one and perhaps other conceptual models for other areas. So you'll need to be able to draw this out and with these different features on it. This is a video that's on, should be a link on Canvas. It's also on YouTube. And I think it's 4-minute video, and I go and sketch it out and describe it. So that could also be a resource, but I want to go through here and do this conceptual model okay, so here are the things that we need: geology, water table, flow system. All right, so let's do the geology first. We got these three. Well, I think they're really going to be 4 units, because one of the things that I think I didn't point out, but when we saw the permeability profile, hydraulic conductivity profile through the saprolite with the different graphs, we went through the transition zone, and then it went. Let's take a quick look at it, because it's. I said this one. So we get through the transition zone, and we're back to around 10 to the -6. Okay, this is rock, and it's fractured rock, and the fractures give it this hydraulic conductivity. As we go down deeper, the frequency of the fractures drops off. There are fewer fractures, they're not as well connected, and then the hydraulic conductivity tends to go more towards what the intact rock is, which is 4 orders of magnitude less. So it would be like down here. Okay, so once we get down here someplace, this curve goes down here. So we'll have 4 different units. The saprolite, the transition zone, and the fractured rock, and then the sparsely fractured rock or intact rock. Okay. So we'll start off with our cross section like this. And the geology, the saprolite we're going to have going underneath the stream, and the contact between the saprolite and the transition zone is going to be somewhat variable. Okay, so this we would have as saprolite. Okay. So those are the different geological means. Here's the transition zone. And we've got some fractures here below the transition zone, and we go deeper, we get fractured rock into impact rock. Okay, so that's the geology. And then the water table. Well, the water table, this is a local, well, the water table is going to start here at this stream. And we're going to have it come up here and then go back down. So we have a groundwater divide. Here's the water table. Here's the groundwater divide. This is the Veda zone. And so the flow system, so here's the water table. So the flow system, we're going to have, if we have some rain, we'll have infiltration into the Veda zone. And infiltration is generally going to be vertically downward. It doesn't necessarily need to be exactly vertical, but it's driven just by gravity downward. So we can just draw it, more or less going down like that. And then the flow system, the flow path, so it's going to go down and maybe go in the transition zone a little bit, come up like that. A flow path like this is going to go in, and remember, these flow paths can't cross. So there's a flow path that just stays in the saprolite. And then another path that goes here and comes down and gets in the transition zone. Transition zone, we think, is a little bit higher permeability than the rock around it, so it'll be preferential, but it's not all that high. And at some point, we're probably going to have the flow get into the fractures in the rock. So we have it go down like this, through the fractures, and then come back. Okay, so those are the different potential float paths that we could have. This is the divide, so we can have then, flow that goes like that. So, this cross section with these flow lines that I've been drawing all semester, it's modified a little bit here because of the geology, but it's quite, quite similar to what we've seen. So we need to have some dimension here. Some scales. So one important scale will be that. Okay, and that scale, the one way to think about it is to say, okay, well, if we figure that this come like this, and then there's a flow system that comes like that. So this is the neighboring stream, and what's called the drainage density, the spacing between streams in the Piedmont, it's roughly 1 kilometer. Okay, so given that, this spacing here is around 1/2 a kilometer, which I guess is what, about 1,500 feet. Go. Okay. So let's do the dimensions in a different color. So 1,500, and here, what did we say depth to water? What do we say typical depth to water was? 20 to 60 feet. 20 to 60? That seems good. 20 to 60 feet. That would be an important scale. I guess one thing too that we might do, this isn't in the video, but maybe you draw this like this. Go with one of those insides stream channels. And you know what I'm talking about? If you're out hiking around here and you just come across a stream, in many places it's cut down like that. Okay. So I guess another scale is going to be this. Depth to rock. So maybe I think what it says up to 150. So maybe say I think I said on the previous slide 10, something like that, 20 maybe to 150 feet. These are typical. There are places where where the rock is at the surface. So that would be, I mean, what we're trying to do here is come up with what the typical expectations are at any given place, right? There'll be exceptions, but this will allow us to kind of train our expectation. All right. So those are some scales, and we need properties. So hydraulic conductivity. What do we have for hydraulic conductivity of saprolite?
10 to the -6.
Yeah, so let's say K is 10 to the -6 meters per second, plus or minus 10 times. Okay, that's pretty reasonable, I think. And then fractured rock, the shallow fractured rock, similar. Similar, 10⁻⁶ meters per second, plus or minus. And transition zone. This would be your. Five times 10⁻⁶ meters per second. And then down here, down in the impact rock, this would be more like 10⁻⁻10 meters per second, also plus or minus. Okay. So that's hydraulic connectivity. Then another important one would be the porosity. So porosity, impact rock, 1 to 2%. Let's use N for porosity, 0.0102. Fractured rock. Yeah, so it would be like 0.01 or maybe 0.03 or 4, 5, called 4. Turns out fractures are pretty narrow and they don't contribute much to the porosity. Up here, the saprolite is going to be 0.4 to some that's 0.6. And then transition would be somewhere in between. And it's going to be, say, 0.1 to 0.4. That identifies the transition zone a little bit better. Okay, so those are geology, water table, flow system scales, and properties. So this will give us, when we first would go to a site and do some work, this would give us a place to start thinking about what might be there. And that's going to be an important thing to get started. All right. We're good. I'll see you next time.